Hi guys, welcome to today's recording. We'll be going through the 2021 NCEA Level 2 Structure and Bonding exam. So let's get started. So first question is looking at the types of solid. So for the type of solid questions, you just need to know your basics. When you got non-metal elements like these, so this is molecular solids. Molecular. Let's make this a little bit darker. Molecular solid, and then copper, this is made of metal, just metal on its own, so this is a metallic solid. Excuse me. And graphite, this is giant covalent network, okay, because it's just made of carbon atoms. So the type of particles that make up an oxygen solid is molecules, and the force of attraction is intermolecular forces. And this is really weak, and so have really low melting point and boiling point. Copper, this is made of metal atoms, or just atoms is fine. And graphite is made of carbon atoms. Okay, so this is made of for metallic solids. It's held together by metallic bonding, and with graphite, giant covalent network is held together by covalent bonding. So you just need to look at what type of solids you have. If it's non-metals, then it's molecular. If it's metals, it's metallic. If you have a metal plus a non-metal, then it's ionic. And then giant covalent network is just your silicon dioxide, graphite, and diamond. Okay, so just make sure you know the basics. Next part here, so we got copper, used for electric wiring due to its ability to conduct electricity and be straight into wires, which is ductility. So explain both of these properties. Okay, so what you need to understand, for anything to conduct electricity, you need free moving electrons or free moving ions. And for copper solid, you will have delocalized electrons. So what it means is that you're just going to have electrons that are delocalized. It's just going to randomly move around. So this is your delocalized electrons, which means they can be used to carry charges. Okay, so that explains that. And then the fact that it can be stretched into wires is that if you look at the bonding that we're doing here, metallic bonding is a force of attraction between these electrons and the positive nucleus. So with metallic bonding, it's non-directional. So what that means is that the electron that are highlighted could actually bond with any of the protons that I've just drawn here, because there's no limit to which one it can bond to, and it doesn't have to go in a specific direction. Okay, so that means these particles, so the reason why they're malleable and ductile, so you got these particles that are held together by just this force of bonding, and then you can press it, you can stretch it, you can do whatever you want to it. They will still stay intact because they can move around each other without disrupting the metallic bonding, which is what's holding it together. Okay, so if we look at the answers, so here it is. So you got 3D letters held together by non-directional bonding. So what it means is that the non-directional nature, the particles can move past one another without changing, without disrupting the bond. And the delocalized valence electrons, that means you got free moving charged particles which can carry charges. Okay, the solid section is just something that's that's guaranteed gonna come up. So people in my students in my class, in the classes I teach, I've sent them through some of the I compiled together like a list of all the things they need to know. So something like that is quite. What I might do is I might share that particular document. I'll probably figure out a way to put in the comment section or the description or something, so you can have a look at that yourself. Okay, next one. So what does it say? Liquid oxygen stored in oxygen tank, blah 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 blah. Oh, there we go, graphite. So it says oxygen, which is a molecular solid, turns into a gas at -183. Into a liquid, from liquid to gas, whereas graphite heated around 3,600 degrees in order to go from solid to gas. So they're just asking you the large difference between the temperature at each substance turning into gas. So they are asking you why, O2 versus carbon, which is, graphite, why does the melting point, in this case boiling point, differ so much? Because this is made of molecular bonding, and this is giant covalent network. So this is held together by intermolecular forces, whereas this one is held together by covalent bonding. So the intermolecular forces is really weak, whereas the covalent bonding is very strong. So in order to turn something into a gas, you have to completely break the intermolecular forces. So this one is not going to take too much energy, whereas this one, if you want to break all of those covalent bonds at the same time, you're going to require a lot of energy to do that. Okay, so if you look at the NCEA answers, this is what they came up with. So oxygen is a molecular solid substance, weak intermolecular forces, requires a low energy, therefore the boiling point is low. Whereas graphite is a giant covalent network, layers of carbon atoms. It's really important that these things I don't really mention. It's good to talk about them. I say your graphite is a 2-dimensional covalent network, whereas your diamond is a 3-dimensional network, which is held together, each carbon bonded to 4 other carbons, whereas your graphite is 1 carbon bonded to 3 other carbons, but they're held together by strong covalent bonding, and that requires a lot of energy to break this force of attraction in order to melt it. Okay, so pretty straightforward here. Very, very typical sort of questions, especially with 2.4. Literally before the video, someone at my school asked me at the school, which standard, sir, do you think is the hardest? And I literally said it depends. Some people find organic the most difficult. Some people find structure bonding the most difficult for some reason. So it's more, do you just a matter of which one are you, more confident in due to the amount of content, or how you've been taught, just how you, if you clicked, certain standards are just much easier. All right, number 2. Let's have a look at this. Lots of blast. I look at this. This is an endothermic reaction because this number is negative. So what are we looking for? Which diagram represents the reaction profile? So it's going to be this one. Why is it that one? How do we, on the diagram we chose, clearly label the change in enthalpy. So the change of enthalpy is from here to here. Okay, so this is change of enthalpy. So why did we choose that one? Because the negative change of enthalpy, so this number here is negative, so that means it's XO, and then you can just remember this is XO, this is endo. What is XO? It just means energy has been released, so that means your products have less energy because some of the energy have escaped, so the products have less energy than what you had before. Okay, so that's that. Let's look at this one. Many rock engine run fuel rich blah 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 blah. I'm just reading through. Okay, so we got, there's a lot of grams of kerosene fuels loaded into first stage. However, only 75% of this is combusted. Calculate the energy produced by the combustion. Okay, so we know, so this is something that you straight away I would recommend people to identify this. Okay, so they gave us the grams of kerosene fuel. They told us that 75% of that burns, and they asked us to figure out how much energy is produced. So you need to straight away identify that this is the only species that I got given, and that is the only species I'm interested in. And this is where you need to, just helping you break it down. Just from the equation, you can see 2 moles of kerosene releases negative 15800 kilojoules of energy, right? So that means 1 mole of C12H26 is going to release half of that, which is negative 15800 divided by 2, which is going to be negative 7900 kilojoules of energy. Okay, so because we want to know how, so this is 1 mole, so we know 1 mole is 7,900 kilojoules energy is released. We know we have this many grams, so we can convert that grams into mole. Okay, so we know we have this many grams but we know that 75% of it burns, so we can figure out the grams. So this is going to be 1920000 grams, and then I can convert this to moles, because whenever you know the mole in chemistry, you know the what do you call it? You know the mole, because grams to mole is just by using the molar mass, and something that we normally do in chemistry is every single number that you've seen in this particular question, we have used it. We used it once. It's very rarely that we need to use a single number twice, and it's extremely rare that we give you a number that you don't need to use to calculate. Okay, so it's very, very rare. So this is 11294 mole. Okay, so come back here. So 1 mole is negative 7,900. I have this many moles, so just 11294 times negative 7900, and that's going to give us 8.92 times 10 to the power of 7 kilojoules of energy. Okay, so or you can write it out as 892 with 5 zeros at the back, and that's fine as well. Okay, very typical question, nothing out of the ordinary here. All right, here, so we got kerosene is a non-polar substance. Use the bonding to identify if the solubility in water and cyclohexane. So you need to understand that water is a typical, it's a polar solvent, and cyclohexane is a non-polar solvent. Okay, so like dissolves like. Now this is where you don't just go on like dissolves like, and therefore this is non-polar, so that will dissolve in cyclohexane because like dissolves like. That is not a sufficient explanation. So you need to understand that when something dissolves, it's looking at, if, like say for example, why does salt dissolve? The reason that table salt dissolves in water is because when you put that in there, the new force of attraction between the ions of salt and the water is, so the new, the new chemical interactions that we're dealing with is stronger than what we had before. So they break and become something stronger. Okay, so if I put the kerosene, if I put CH1226 with water, this is not going to dissolve. The reason why that doesn't dissolve is because the water molecules are polar. So the force of attraction between water molecules, this side's negative, this side's positive, this side's negative, this side's negative, this side's positive. The polar interaction between the water molecules is very, very strong. So, and then your C12H26 doesn't have the positive ends and the negative ends. It's not going to be able to mingle with these H2 molecules, so therefore it doesn't dissolve. So, and how you could explain it, obviously I have the answer underneath, but how you could explain it is just talk about the existing force of attraction is already very strong, and then the C12H26, supposedly the new force of attraction that could happen is not strong enough to overcome the existing one, so it doesn't do anything. Okay, so but if you put C12H26 with cyclohexane, and what's going to happen now is that yes, these guys they can interact with each other because they're both non-polar. So if you put it in there, they can mix together because a new force of attraction, which is the one that we're looking at on the screen, is strong enough to overcome what we had before, because the force of attraction of the existing what we currently have is already pretty weak, so they don't really mind if you introduce a new one. Okay, so the really important thing here, guys, first of all, identify the polarity of the solvents. Now here, so the attractive force it forms with water molecules is weaker than the existing force of attraction. Okay, so it's just saying the interaction between the solvent, which is between the kerosene, the kerosene and the kerosene, and then the solute, which is the water and the water. Sorry, not the water. The solvent is water and water. Sorry. So they're saying in this particular part, they're saying water, kerosene. They're saying this is currently the existing force of attraction, And then if you mix the kerosene in here, that's not going to dissolve, because what we already have right now is stronger than what it would become. Okay, now for the next part is that as both kerosene and cyclohexane are non-polar, so the attraction force between is not strong enough to overcome the existing force of attraction between each substance. So that just means right now we got kerosene, and we got cyclohexane, and then I'm just saying, all right, so if we mix these two together, then we can have kerosene mixed with cyclohexane. This is stronger than what we had before, and that will dissolve. Okay, so it's very important. Don't just talk about like dissolves like. You actually need to understand when something dissolves, it's because the newly produced force of attraction is stronger than what you had before, and that is why they dissolve. Okay, it's very, very important. Next part, Lewis diagram. That was a short question. I swear these exam questions are getting shorter and shorter. Alright, so let's go. So Lewis diagram, very easy. ASF3. So you just need to find these guys on the periodic table. So AS is where is AS on the periodic table? Let's just do that first. So this would have, I think it's group 15 from memory. So this will be 5, this will be 7, this will be 7, this will be 7, it's 8, it's 8, it's 8, it's 8. So this is the group number, you know, group 15, group 17. So this is 3, this is 26, 32. So 32 minus 26 is 6 electrons, so that means you have 3 bonds. Now, I'm not going through these as thoroughly as I normally would, because I've done this so many times. I strongly recommend you to look at my 2018 videos, and that's when I break down a lot of the stuff into great details. So, you know, very, very thorough explanations. But for these, because, you know, I've done quite a few years of examinations, it's all the same questions. So just make sure you can have a look at those. All right, 3 bonds, that just means AS, 3 bonds, 1, 2, 3, F. Boom, 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 boom. Make sure every single fluorine has got 8 electrons, and then we got 2 left. And over here, so this is the trigonal pyramid. All right. Oops. Now H2S is going to look like this. This is bent. F2CO. Remember, your C always goes in the middle. And this is where people sort of don't understand, like, how do you know C goes in the middle? Because C always bonds 4 times, O always bonds twice, hydrogen and fluorines and chlorines, and then only bond once, and that's how I know the carbon must goes in the middle. Okay, so make sure you put the valence electrons, you know, around like that. And this is trigonal planar. How do we know this is trigonal pyramid, bent and trigonal planar? Because for ASF3, this is 1, 2, 3, 4 regions, only 1, 2, 3 connectors, so that's trigonal pyramid. This one's 1, 2, 3 regions, all of them are connectors, so it's trigonal planar. This one's 1, 2, 3, 4 regions, tetrahedral arrangement, but only 2 of them are connected. That's why it is bent. Okay. Next one. So explain the difference in shapes and bond angle and that are colored red in each. Okay, so you just need to look at this. So this nitrogen here right now has 1, 2, so this has 2 regions of electron density around the nitrogen. Okay, well, this nitrogen has got 1, 2, 3, 4. So this one has 4 regions of electron density, and for these ones, both bonded. So you can hold up your arms, one to the left, one to the right. It's exactly like that. So your torso is the nitrogen in the middle, and then your oxygen and nitrogen are your left and right hand side. So that can tell you that this is going to give you, you know, according to the electron pair repulsion theory, what these oxygen and nitrogen will do. They will position themselves as far away as possible, and that will give you a linear shape with 180 degrees. Whereas this one, you got 4 regions. Okay, so these 4 regions here are going to position themselves as far away as possible, but one of those, which is this guy over here, we can't physically see that because it's electrons only. So you got 3 bonded and 1 lone pair. So, and these guys will position themselves as far away as possible, which will give you a tetrahedral arrangement. And people always get a bit confused about tetrahedral arrangement, tetrahedral shape. The tetrahedral arrangement, it just means that you got 4 corners, okay? But because one of the corners is a lone pair of electrons, you can't see that. This is why this is a trigonal pyramid shape. The final shape, you know, if you look on a powerful microscope, you're going to see the trigonal pyramid shape because you can't see one of the corners. Okay, so if you look at the answers here, it's the same thing. So 2 regions, whereas the other one has 4 regions. So they always want to minimize repulsion by getting as far away from each other as possible. So one is linear, bond angle 180. The other one is tetrahedral arrangement, and then 109.5 degrees. So whenever you have 4 things, it's always tetrahedral arrangement. Okay, so you could have, you know, the one that we did just now, you know, H2S, you know, this one is also tetrahedral arrangement, 1 2 3 4. So this bond angle is also 109.5 degrees. You know, it's a little bit less. The more chemistry you learn, the more understanding you have. It's actually not exactly 109.5. This one's probably looking at 105 degrees, but you only get 12, so we're not gonna make you remember that. It's just that, you know, it got 2 bonding. Sorry, for the N2H4 it has 3 bonding, one lone pairs, so they're gonna have a trigonal pyramid shape. Okay. All right, calculations. So whenever you see a table like this, guys, this is your bond enthalpy calculation. So this is where you just need to straight away, just don't even doubt yourself, just write this down. You need your total of bonds breaking, add that up, minus your total of bonds making. Sorry. Okay, so you've got to break physical bonds and then make chemical bonds. So they've done that for you, which is really nice. So you can see 1 2 3 4. So what did I break? So I'm just going to do it here. I'm going to break 4 CH bonds. So each CH bond is, where is it? Oh, we don't know. We're actually trying to calculate it. Okay, so that's fine. So it's 4x. Let's make that x. What else are we breaking? We're breaking 2 O2. So each O2 is this. So we're breaking 2 of them, 2 O2, and that's going to be 2 times the numbers right here, 495. So that's my breaking. For my making, I'm making this and this. I'm making CO2. So in my CO2, I have 1 CO, 2 COs. So this side, let's use a different color pen. So I'm going to times 2 times, where's CO? 8. CO. So this is 2 times 805. And then this one here, so I need to make 2 water. So I need to make 2 of these. So in each water, I have 2 OH bonds. So in 2 water, I have 4 OH bonds because there are 2 moles of water, and each mole is 2 OH bonds. This is going to be 4 times 463. And what does the enthalpy number equal to? Is right here, negative 802. So there you go. So negative 802 equals 2 times 495 plus 4x minus 2 times 805 plus 4 times 463, and then you can do your math and then calculate x. X equals 418 kilojoules per mole. Okay, so this is purely mathematics. Like I always say, if you can't do math, you're in the wrong channel. Okay, so I'm here to teach you chem. If you can't solve a simple algebra equation like that, then I don't know why you're learning chemistry at all, because that should be really easy. All right, next part. Calculate the mass of methane required to blah blah blah. Okay, so we want to release 1,660 kilojoules. Okay, so that means we want to look at. So we want to release 1,660. So what are we looking at? CH4. Okay, so we're interested in CH4. Let's look at this. Let's write this down first. So we know 1 mole of CH4 releases 802. I want to know how I'm now releasing 1660 kilojoules. How many moles do we have? So you need to use 1660 divided by 802, which gives you 2.07 moles of CH4. Okay, so how many grams is 2.07? So N equals small m divided by big M. M equals N times big M. So it's 2.07 times 16, 33.1 grams. Okay, so here's what I meant again. You see that number, you see this number, you see this number. Every number that you've been given was used once. Okay, so there you go. Last question. Determine if these things are polar or non-polar. All right. So this applies in year 12. Okay, year 12 only. When you see lone pairs electrons above the central atom, straight away this is polar. Because what it does is that this lone pairs is not bonded, so you don't see it, and that will, you know, it will make the shape asymmetrical and also exert more repulsion forces. Now for BCl3, so these three things are exactly the same, so it's just like that, you know, perfectly divided by 3. So this is going to be non-polar because the dipoles cancel each other out. This is going to be polar, this is going to be non-polar. So what you need to talk about first, you need to talk about the polar bonds. So why is PCl bond polar? Why is BCl bond polar? So these two bonds are always polar because they have different atoms. When you have different atoms, you will have what we call significant difference in electronegativity. So what that means is that one of those atoms is going to want electrons more than the other, so they unevenly share those electrons. Okay, so when you create bond when you create polar bonds, you make bond dipoles. Okay, so what is bond dipole? The bond dipole just means you got one side that's positive, one side that's negative. That's what it is. Poles. Dipoles means two. Pole means charge. So it just means you created two charges. Okay, but then PCl, this is arranged in a asymmetrical trigonal pyramid shape. This shape is asymmetrical, so that means these bond dipoles do not cancel each other out. But then BCl is arranged in trigonal planar, and that means they will cancel each other out. So all the poles are gone, then the thing's non-polar. Okay, so first thing first, always talk about the bonding. And then, because you can't just say, oh, the bond dipoles, oh, the shape is asymmetrical, so the bond dipoles don't cancel each other out. So how the heck did you, where did the bond dipoles come from? So you actually need to explain what the bond dipoles are, and then explain. Okay, so due to the trigonal pyramid shape, which is asymmetrical, means they don't cancel out, whereas the other one, it will do. Okay, so there you go. I think that's the end of the question. Yes, it is. That's the end of this particular exam. So hopefully this was helpful. So all the best with the upcoming examinations, and subscribe if you haven't. Share the videos to anyone that's struggling in chem, and I'll see you guys next time. Bye bye.